Good morning. My name is Fernando. I'm a professor at UFMG Brazil, and today I will present to you AutoParBench, a work that I did in collaboration with Gleison Souza from UFMG and Xunhua Liao from Lawrence Livermore. The main goal of this paper is to bring forward a framework that allows direct comparison between the output of automatic parallelization tools. To understand this goal, let us first explain what is an automatic parallelization tool. In the context of this work, we shall be talking about programs written in C and of tools that annotate these programs with OpenMP politeness. Examples of such tools include ICC, DownCC, Rose AutoPar, Cetus, Mercurium, Pluto, and TaskMiner. In particular, in this paper, we have been able to directly compare 4 of these tools: ICC, DownCC, AutoPar, and Cetus. A second important aspect of this work regards what we mean by direct comparison of tools. By direct comparison, we mean that we want to be able to convert the output of these tools, in this case annotated programs, to a common representation. If we can translate their outputs to a common representation, then we can compare these outputs. Our intention, in the end, is to use this capability to compare the output of these auto-parallelizers to find bugs in some of them. If they produce different outputs, then it's possible that some of the divergent tools have bugs. With this goal in mind, that is to find bugs in auto-parallelizers, this paper brings forward a number of contributions. First and foremost, we have this common representation that allows us to compare the output of auto-parallelizers. This representation currently is based on the JSON format, but nothing really hinders us from using something else like YAML, XML, or even a DSL. Then we have all the infrastructure to convert the output of different and well-known tools into this common representation. And we have the infrastructure to perform comparisons using this common representation and then generate reports that help developers to find bugs. And to find bugs, we have designed a protocol to analyze reports so that warnings more likely to be actual bugs can be analyzed first. Together with all this, we have a reference collection of manually annotated benchmarks, which we can use as a ground truth. This collection currently has 99 programs, which together gives us almost 1600 annotated loops. Some of these loops contain no data races, so they should not be parallelized. Finally, we have been able to use our framework, AutoParBench, to find bugs in different tools. We have reported several warnings and got confirmation for 3 bugs in ICC, 2 in DownCC, 4 in AutoPar, and 2 in Cetus. Some of these bugs have already been fixed. To put this infrastructure together, we had to overcome a number of challenges, which I shall discuss now. The key problem that we faced is that there are different ways to parallelize programs, and they might all be correct. If we flag them as potential bugs, AutoParBench would not be useful because its users would be overcome with warnings. We'll go over some of these challenges then. For instance, the same program may be parallelized in different ways. Consider this program, for instance. The for loop is a map, and each iteration of it can run in parallel. We could transform this program so that it runs in a graphics processing unit, for instance. But we could also parallelize it so that it runs in a CPU with vector instructions. And these 2 ways to parallelize the program are correct. So if we compare the output of tools that produce these programs, we still need to somehow understand that both outputs are correct. Another challenge is the fact that a program might run in parallel under some circumstances, even though it contains data dependencies. As an example, consider this program. The program might contain data dependencies if the dest and source arrays overlap. This overlapping is possible in C. And yet, it's possible to use guards to ensure that the program only runs in parallel when no data dependencies occur at runtime. Some tools like downcc do it, for instance. Another challenging issue is the fact that different loops in a loop nest can be parallelized. For instance, in this program, we have two loops. An autoparallelizer could choose to parallelize both, like in this example, or it could choose to parallelize only one of the loops, and it's okay. Maybe a cost model indicates that only the outermost loop should be parallelized, for instance. Another challenge concerns data movement. OpenMP provides more than one way to indicate that data must be moved from host to accelerator. For instance, let's consider how we could accelerate this program. We see that variable tmp needs to be privatized and that the array needs to be moved onto the accelerator. That's a way to annotate the program. And that's another way, which, although synthetically different, still encodes the same semantics. Another hard challenge is the fact that OpenMP pragmas can use symbolic expressions, that is, expressions that refer to the names of variables declared in the program. For instance, let's consider this program, which is embarrassingly in parallel. On the right, we see a way to parallelize it. In this case, the map directive uses the name len, which is defined in the program. But this name encodes a constant, and a simple constant propagation would already let us write the equivalent program on the right, and a tool that compares both programs must be aware that variable len is indeed the constant 100. Finally, we have this last challenge: autoparallelizers can transform programs. For instance, consider this program, which is also embarrassingly in parallel. A compiler like ICC is able to merge both loops into a single loop and then parallelizes this new loop. Our evaluator needs to take this possibility into consideration when comparing the output of ICC with the output produced by other tools. Now I will show how we have dealt with these challenges when producing an infrastructure that let us compare the output of autoparallelizers. The key idea to overcome the challenges was to come up with a common representation to the outputs produced by different AutoParallelization tools. We call this common representation a JSON snapshot because we use the JSON format to implement it. An instance here is an example of a JSON snapshot. This snapshot can represent this program on the left, but it can also represent this new program which encodes the same semantics. Currently, we have a general class of JSON objects with 10 fields. And we have a special subcategory of objects which encodes, in addition to all the common features, also features that are exclusive to loops. The goal of the JSON snapshot is to normalize the output of different tools in a way that the output of these tools for the same program written in C can be compared. Today, we can produce snapshots for 4 tools: ICC, AutoPar, Cetus, and downcc, and 4 programs in a reference collection. To produce these snapshots, we have translators. We have currently 2 types of translators. We have a translator that is exclusive to ICC. That's because ICC outputs is binary, so I need to extract its annotation out of that format to create a snapshot. And we have another translator that's common to all the tools that are source to source. So it parses a C program annotated with OpenMP pragmas and produces the snapshot. Finally, we have an evaluator that compares 2 snapshots and produces a report. This report basically groups parallelization decisions in false or true positives and false or true negatives. Once we have JSON snapshots for the annotated programs produced by 2 tools, or by a tool and a human, or 2 humans, whatever, we can compare them. The result of this comparison is a graphical report. This report is a matrix of colored squares. Each square refers to a particular annotated loop. Light gray denote true positives. That means that both JSON snapshots encode the same parallelization decision. We can also have 4 other possible results. Different parallelization means that our infrastructure does not know how to compare automatically the output produced by the different tools. A false negative means that the reference snapshot has annotated the loop and the parallelizer hasn't. This might indicate that the parallelizer is missing opportunities to speed up loops. A false positive means that while the reference loop is not annotated, the tool has annotated it. That might indicate a bug if we know that the reference loop contains a data race, for instance. Finally, a true negative indicates that the tool refused to annotate a loop that, indeed, was not expected to be annotated. To maximize the number of true positives, the evaluator can recognize a number of semantic equivalences. We recognize a number of equivalences like these in the paper. For instance, separate occurrences of 4 in parallel in the same loop are equivalent to parallel 4. Making explicit every implicit data sharing clause. For instance, AutoParBench sets as private the loop index variable unless this variable is explicitly annotated with a different data sharing mode. Reduction operator minus is normalized into the plus operator since they are semantically the same. And constant variables are replaced with their values whenever possible. To help in finding bugs in autoparallelizers, AutoParBench contains a reference collection with manually annotated programs. Every loop can be was parallelized. Notice that these annotations are applied whenever possible, even when it's not profitable to parallelize the loop. Currently, we provide 99 annotated programs, and these programs contain 1579 loops that are either annotated or marked as negative examples, which should not be parallelized because they contain data races. The programs in the reference collection come from 3 main places: from DataRaceBench, from Rodinia, and from NAS. Some of these programs were already annotated with OpenMP pragmas, others we had to annotate ourselves. Most of the programs in the reference collection are small. That means that almost 80 of our benchmarks have less than 100 lines of code. And a few benchmarks are large. 9 of these benchmarks have more than 1,000 lines of code. These are mostly programs coming from Rodinia. Similarly, most of the benchmarks contain 1 or 2 loops, that's less than 10 loops. In particular, 78 benchmarks have less than 10 negative loops, meaning that these loops cannot be parallelized, and 87 benchmarks have less than 10 positive loops, meaning that these loops should be parallelized. Now I will show a few use cases of AutoParBench. In particular, I will show some bugs that this framework has helped us to uncover. We start by showing how we can use AutoParBench to compare tools. In this case, we shall have 2 comparisons involving different tools. First, we will compare tools that target multi-core CPU systems, namely ICC, Cetus, AutoPar, and the reference collection. Notice that we will consider 2 versions of ICC. The first, called ICC Full, tries to annotate as many loops as possible without using a cost model. The second version of ICC, that we call ICC Cost, uses the cost model to annotate loops that this cost model deemed profitable to annotate. The second comparison involves tools that target vector machines. In this case, both work, GPUs or CPUs with vector instructions. Here we have the first result of this comparison. We're comparing all the tools that we have with the reference collection. If we recall, these pictures have 1 square per loop that is comparable. The bottom line is that the lighter the figure, the closer it is to the reference collection. You might also notice that these comparisons don't use all the same number of samples. That happens for 2 reasons. First, 2 of the tools, DONCC and ICC, SIMD, use a different part of the reference collection, which refers to vectorization. This subset of the reference collection contains only 63 loops. The other 4 tools use the part that refers to CPU multithreading. This second subcollection contains 1579 loops. Second, some tools have not been able to process all the files. They would crash when processing some of these files. For instance, out of the almost 1600 loops that we gave to Cetus, it could annotate 430. This said, notice that most of our results are either true negatives or true positives, meaning that the tool has produced outputs that were expected in the reference collection. This table summarizes the result of the graphical comparison. From the notion of true and false positives or negatives, we can build the 4-class comparison metrics: precision, recall, accuracy, and F1 score. But the really interesting metric in this context is what we call the weighted F1 score. This metric tells us how close a tool is to the ground truth. If the weighted F1 score is 1, then the tool is doing exactly what the reference collection expects. So basically, the weighted F1 score is the F1 score multiplied by the fraction of programs that the tool has been able to process correctly. In our context, using the weighted F1 score is better than using the F1 score because some tools like Cetus can process only a small number of programs. However, once we take this fraction into consideration, we see that the tool is not that close to the ground truth, as most of the programs remain unprocessed. If a tool is far away from the reference collection, it might contain bugs. So we have analyzed the warnings that we got with AutoParBench, and we have reported some of these warnings to the developers. However, we get too many warnings. To deal with them, we had to prioritize them. We have designed a protocol to prioritize warnings that are more likely to be bugs. This protocol groups bugs into 5 layers. Here they are. First, the first tier contains situations in which the tool crashes. In this case, obviously there is something wrong with it. The second tier contains programs that, once parallelized, produce results different than what the reference input does. That's a strong indication of a bug. Then we have false positives. The tool has parallelized a loop that contains maybe a data race, for instance. Then we have different parallelizations. Our experience shows that usually these cases are not really bugs, but we still have to evaluate them. Finally, we have false negatives. False negatives might indicate a performance bug. That is, the tool is refusing to parallelize a loop that's clearly parallel. That's the summary that we got when we compared the different tools with the reference collection. You will notice that we got warnings in all the tiers. However, some of these warnings encode the same bug. Here is an example of a bug that we have found in Cetus. For this program, the reference collection expected a program equivalent to this code below. However, Cetus ended up producing a reduction after a transformation that led to a runtime error. This program produced a false positive using ICC. That means that the reference collection does not parallelize it, but ICC has transformed it to run in parallel. The program still produced the correct output when it ran. However, Intel Inspector does point a data race in the program. We have reported the bug and it has been confirmed. And here we have another bug that we found in DownCC concerning this program. In the reference collection, we have that TMP should be privatized to avoid a potential data race. However, the output produced by DownCC did not contain this privatization. This bug has since been fixed. With these bugs, I conclude the presentation of our paper, which has introduced AutoParBench, a test framework for autoparallelizers. These autoparallelizers annotate programs with OpenMP, and we can compare them by converting this output to a common representation called a JSON snapshot. AutoParBench has already been useful to report a number of bugs in different tools. Today, it's available at this location, and we welcome interested developers and researchers to write to us with questions, comments, and suggestions. Thank you very much for your attention.